Y'all ready for math? Y'all ready for math? Welcome back to another pre-calculus honors mathematics virtual lesson. Okay, you should have handed in that related rates take home. Actually, I think it's due today, right? So this is Wednesday's lesson. So tonight by midnight, please have that into me. We got one more chapter to do. Okay, this chapter is going to take us up until, right before AP exams. Just so you know, in here, we're probably going to be doing some lax stuff for those 2 weeks of APs. I think I'm going to give you big set of review sheets I normally had set up for the final and have you guys just work on it. Really like a 2-week assignment. That won't take 2 weeks, okay? Because you guys got to focus on your AP exams. So we'll be lax then. And then after those 2 weeks, we'll come back with a fire because we still have some stuff to do. And I think we're going to have some extra time. I might be able to throw some extra things in there. But let's not worry about that yet, okay? Let's talk about the next chapter because we've been working on chapter 3 for a while, right? Applications of the derivative. We talked about curve sketching. We talked about optimization. We talked about related rates. And now we finally moved into chapter 4. And here's where stuff gets really good, okay? The derivative is really cool, really interesting, extraordinarily important as far as calculus is concerned. But today in chapter 4, we start talking about the indefinite integral. And if you thought the derivative was popular walking around the calculus campus, OMG, did you see him? He's here. The derivative just waltzing around, strutting his or her stuff. But then the integral comes in, and if the derivative is the ruler of calculus land, then the integral is the emperor of calculus land. Okay, very, very important. The integral we're going to start talking about today. Not so easy. Differential calculus, normally people a little bit more successful with than integral calculus. Okay, so we'll get as much of this done for this year, so that'll help you out as far as next year is concerned. So an integral, okay, is actually known as an antiderivative. So before you start freaking out, the integral is going to be more difficult, that's what he just said. If you didn't like differentiation, okay, maybe you're like, I hate derivatives, I can't stand them, and you had like a big protest outside of Glenn before the whole COVID thing, and you're like, I am anti-derivative. Well, if you're anti-derivative, that means you're actually for the integral, okay, because the integral is the antiderivative. So just a little bit of math humor right there. You used to something like this. You used to seeing y equals 3x cubed. And then I'll ask you, hey, what's dy over dx, which we know really represents the derivative of y with respect to x. Classic power rule action here. Drop it like it's hot, drop it like it's hot. We get 9x squared. And I like to say the process of moving down a step, I like to say is taking a derivative, which is differentiation. Remember, the process of taking a derivative is known as differentiation. But now we're going to go backward, okay? We're going to start down here, and we're going to know what the derivative is. They're going to tell you dy over dx is equal to 2x, and we're going to have to head back upward and figure out what y is equal to, okay? And that means that's the process of anti-differentiation. That's the process of integration. All right, so integration is anti-differentiation. Sorry, my nose is a little snotty today, okay? It's supposed to be a beautiful day, though, so I'm going outside anyway, so my nose is probably getting more snotty later. That's disgusting. Okay, and then you need to think about, well, that's somebody's derivative, right? 2x. So what do you take the derivative of to get 2x? Think about it, okay? Pause the video if you need to. A lot of people are just going to look at it and they'll be like, x squared, I know what I'm doing. But that's an incomplete answer, okay? Because certainly the derivative of x squared is equal to 2x. What if it was x squared plus 5? The derivative would still be equal to 2x, okay? If you have y equals x squared, you know what that looks like, okay? You know that little parabola turning point at the origin. You can see the slopes, okay, are not constant. The only thing constant about the slope is that it's constantly changing. That's why the derivative is variable. But if this was x squared plus 5, it would just be this guy shifted up by 5. And the slopes wouldn't change at all, okay? It wouldn't make a difference. Even if it was x squared minus 8, okay? Then you shift down 8, the slopes would still be the same. So the idea is that whenever you actually integrate, you got to put a little plus c down, okay? And we call that c right there the constant of integration. It's a constant. The constant of integration. All right? And the reason we call that the constant of integration is that, whenever you actually integrate there could have been some constant there, okay? Some constant such that when you take the derivative, obviously, the derivative of constant is always equal to 0, okay? So it'll go away. You could have x squared as the answer, then c would just equal 0. If x squared plus 5 was the answer, c would be equal to 5, okay? So something to think about there, that constant of integration, very important. You know, derivatives are actually a closed set. You give me something, I could take the derivative of it, okay? I can take the derivative of every single function you can think of. Integrals are different. When you integrate a function, it's still unknown, okay, what the actual function is, that you get back when you integrate. You actually need an x and y coordinate that lies on that original function in order to solve for c. In addition to that, there are actually things that are not integratable. We'll learn about a few integration techniques in this class, and we'll use the same techniques next year in AP. Unless you take BC, then we'll talk about a couple more techniques. But there are some things that actually can't be integrated even with any given technique, okay? So integration actually gets a little bit more nasty than you might think. And you got to know about the notation, okay? Remember, calculus is not just about knowing the content, the concepts and stuff like that, the application of the concepts. The notation is important. This right here, you could get this notation. It's known as a differential equation. We talk about that toward the end of the AP curriculum in AB next year, closer to the middle in BC. And we won't see problems like this right away, okay? We'll see the notation for the integral sign, and that's this guy right here, which you might have seen before, okay, in AP Chem. You probably have no idea what it means, but that's the integral sign right there. Believe it or not, people like, it looks like an elongated S. It actually is an elongated S. It stands for infinite sum, something that we'll speak about a little bit later in the curriculum, but we really won't get into it until next year, okay? And what they'll do is they'll ask you to integrate the derivative of something, okay? So you'll integrate that 2x. But just like when you take a derivative, you got to indicate the variable you're differentiating with respect to. When you integrate, you have to indicate the variable that you're integrating with respect to. So that means we put a little dx over here. And what this reads as is it reads as the integral of 2x with respect to x. That's what this guy is. Let's put the quotes here. And you can quote me. We say the integral of 2x with respect to x. With respect to x. Okay, so the integral of 2x with respect to x, or the integral with respect to x of 2x, if you want to say it that way. This 2x, the function that you're integrating, that's the integrand. Not that they really mention that word ever on the AP, but you never know when vocabulary is going to slither its way in there. So I like to talk about vocabulary in here, obviously. That's the integrand, and that's somebody's derivative. That's somebody's derivative in there. Whose derivative? The answer's derivative. You know, if you integrate 2x, you get x squared back, but then we got to put that plus c right there. That's the constant of integration. And the cool thing about this is if you actually take the derivative of your answer, you should get the integrand back, okay? Because integral is, the antiderivative. You could always check your work by taking the derivative of your answer. See if you get the original, thing that you integrated back. So if you take the integral of 2x, integral of x squared plus c, you get 2x plus 0, which is 2x right there. Thus, we know we integrated correctly, okay? If you think you're always going to be integrating 2x, you're tripped out of your gourd, okay? Obviously, it's going to be different functions in there. So I think it's time for Megastar. There was kind of a Megastar over here, but it was like a messy Megastar. Messy Megastar! And m squared. Got to bring that one back in class. When I finally see you all again, might not be until next year. Hopefully it'll be this year. We'll see what's happening. We call this the indefinite integral. There's something known as the definite, the indefinite, and then I want to put integral. That's what happens when you start speaking while you're writing. So let's finish with integral. Okay, there's something known as the definite integral that we'll talk about after AP exams. Then the infinite sum thing will come a little bit more into play. But here we're going to say the integral of some function. I'll say f of x, and then I'll put with respect to x. So this is the integral of f of x with respect to x. There's actually no notation when you take an integral. When you take the derivative of f of x, you get back f prime of x. There's no notation to indicate what you get when you integrate f of x, okay? Some textbooks say if you integrate little f of x, you get back big f of x. Then they put a plus c there. But that's not understood mathematical notation everywhere, okay? So this right here doesn't mean anything. This is just saying you're integrating some function and you're getting some function back. But you have to remember the integrand, that's somebody's derivative in there. Whose derivative? The answer's derivative. So you got to put a little disclaimer. We put a comma and we say where. If you take the derivative of the answer, you have to get back the integrand. Just like over here, you took the derivative of x squared plus c, you got 2x, you got the integrand back. So if you take the derivative of big f of x plus c, you know how to take the derivative of big f of x? The derivative of big f of x is just big f prime of x. The derivative of c is just 0, so we don't put it. And when you take that derivative right here, it has to be equal to the integrand. So big F prime of x equal to f of x. This always confused me when I was your age. It's just a disclaimer. All it's saying is that you're integrating correctly. Okay, right here, f of x in the previous problem was 2x, right? That was the integrand. Big F of x we got back was x squared. And now you can see, if you take the derivative of big F of x, okay, big F prime of x, that's the derivative with respect to x of x squared. They're saying that has to equal f of x, which is 2x in this case, and we do get 2x equal to 2x. We just don't bother with the c because when you take a derivative, you get 0. So this is merely a disclaimer indicating that you integrated correctly. I get it. It bothers people, okay? There's another way to write this. It's a little bit more complicated, but it's actually much simpler to understand. Instead of saying the integral of f of x with respect to x, you could say the integral of f prime of x with respect to x. It's what we're doing, right? The thing we're integrating, it's a derivative, right? The dy over dx was the 2x. That's what we were integrating before. So here, if you integrate f prime of x with respect to x, try to think about what the answer is. Higher order thinking question of the day. What's the answer? And hopefully you're thinking about it in your head. Maybe you put the video on pause, whatever it is. But try to remember the most simple way to integrate anything, that's somebody's derivative in there. Whose derivative? The answer's derivative. So I wonder what I take the derivative of to get f prime of x back. How about f of x? And just don't forget to add that constant of integration. And this is really just an abstract integral. It's all it is, okay? And some people are like, well, what, do you need the disclaimer now? No, because if you were going to set up the disclaimer, you just say where f prime of x is equal to f prime of x. It would be silly, okay? So the reason that this is a better way to set up the notation is because we actually have a notation for when you take a derivative, but we don't have a notation officially for when you take an integral. This is integrating a rate of change, which I believe that you do in advanced placement chemistry. If you integrate the rate at which a quantity changes, you'll actually get the change in that quantity, okay? So if you integrate the rate at which snow falls on the ground, you'll actually get the change in the amount of snow that's on the ground, which will tell you how much snow actually fell on the ground, okay? We'll talk about stuff like that next year. Really, really cool application types of problems, all right? So we'll get there when we need to get there. So that's really the concept behind the integral, and it'll take some time, and this chapter is really going to be mostly mechanical. We won't talk too much about concepts. We'll talk about them more when we get to the definite integral, but even then, it's not going to be so easy to speak about things because you need to know about a couple more levels before the integral is really going to kind of go into place. So we kind of worry about the mechanics now. Let's get that out of the way. Let's make sure you can actually integrate, and then we'll worry about concepts. Just like differentiation, got to make sure you can differentiate, right? We talked about the power rule, the product rule, the quotient rule, the chain rule, and then we worried about applying the derivative afterward. So let's actually talk about low star action. And there are two different types of integration, okay? There's basic integration and there's non-basic integration, just like differentiation, okay? Differentiation, if you take the derivative of a function whose argument is one single x, that's basic differentiation. But if the argument was not one single x, that's a chain rule situation. That's a non-basic differentiation situation. Same thing with integration. We don't use chain rule for integration. We use something known as U substitution. We'll talk about that on Friday, I believe. Today is Wednesday. And that's actually the only technique we'll worry about in this class. Next year in BC calculus, if you take that, we'll do integration by parts, integration by partial fractions, a lot of cool stuff. There's integration by trig substitution. We don't do that in there. Thank God, it gets rough. Anyway, though, a lot of different ways to actually integrate. Let's just talk about basic integration today. And I think you'll find that basic integration, while it might be difficult, at some point in time, you might be like, you know what, I kind of like doing these problems. They kind of rule. I think basic integration rules. Let's write that down. Basic integration rules. And really, I just tricked you into writing that we're going to talk about the basic integration rules. This list will grow. List will grow. So I like to say the list, much like my waistline, will grow, okay? My waistline has already grown to epic proportions during this quarantine. This is a bad, bad thing, okay? I got to get back to exercising. So let's actually just do one rule. The list will grow, but we won't get to the other rules until next week, I think on Monday. And then Tuesday, some more rules. So we'll just have rule number 1 for a while. And it's actually the opposite of the power rule, okay? This is when we integrate. And the power rule is when you want to take the derivative of something like this, 3x cubed right here. Forget about the constant. You could always just pull it to the side. Then you worry about the x cubed. That's one single letter raised to a numerical power. The way we're going to write that up here is we're going to put u to the n. And that might bother some people with the u. The u is just a function of x. If it's basic integration, the u is just x. and the n is just a constant. So maybe integrating x cubed or x to the 5th or x to the 1/2 power, radical x, right? Something like that. But it doesn't need to be one single letter. It could be like, 3x plus cosine x inside u, quantity raised to the 5th power. That's why we leave that u there. Remember that u is just a function of x. Function of x. I guess I could finish writing the word function. I just wanted to write function of x. When it's not one single x, that's a u substitution situation, something we'll talk about in a couple days. But remember, you have to indicate the variable that you're integrating with respect to. And since we have a u right here, we do the integral of u to the n with respect to u, okay? The rules won't be so easy for you to understand at first. It's really the application that's more important, so try not to freak out about that, but it'll take a little bit of time. If you wanted to take the derivative of something like x cubed, you drop the 3 down like it's hot, multiply it by the 1, right? Then you rewrite the inside, and you'd raise it to the 1 less power. You'd subtract 1 from the exponent. We're going to do the opposite of that, okay? This basic integration rule is kind of like the opposite of the power rule for, differentiation. This exponent, we drop it down, okay? We're not actually going to multiply it by the number in the front. The opposite of multiplying is dividing. We're actually going to divide by it. But before we drop that exponent down, we're going to switch the order in which we do these things. Usually you worry about the multiplication, then the subtraction when you actually take a derivative. We're going to do those in opposite order. We're going to worry about the exponent first, but we're not going to subtract 1 from the exponent. We're going to do the opposite of subtracting 1, which is adding 1. Then that new exponent we get when we add 1, we won't multiply it by the function. We'll divide the function by it. So what really happens is if you have u to the n, one single letter raised to a numerical power, rewrite the base, rewrite the one single letter, that's the argument, add 1 to the exponent. Do that first. Then that new exponent, that's what you want to divide by. So you want to add 1 to the exponent, then you want to divide by that new exponent. Then you always have to put plus c. People forget about the plus c. I think one of you guys should invent a stamp, so you can just stamp a plus c after each one of these problems right here. Mostly on tests, you see multiple choice anyway. You don't got to worry about leaving that plus c out. But eventually, when we get into more complicated types of problems that are free response, if you don't have the plus c, it's going to mess everything up, okay? So remember to always add c. Sometimes I say like add cookies, and usually people remember it a little bit better there. We'll do an example of this. Let's do it right now because there's no little disclaimer here, put a little comma, because if anybody who, is good at calculus is reading this, they're like, wait, there's a little exception over here, Mr. Berto. Let's just do a quick example first. Like maybe you have the example of x to the 5th. With respect to x. So the integral of x to the 5th with respect to x is u, 5 is n. Remember, if you got one single letter raised to numerical power, you want to integrate. Don't differentiate. That's one of the most common mistakes. People are like, yeah, 5x to the 4th. I'm the man. No, that's wrong, okay? You differentiated. Don't differentiate when you integrate. Usually with a function, the derivative is not the same thing as the integral, but there is one function where it certainly is. E to the x. We'll talk about that when we get there. But what we're going to do is we're going to rewrite the base. We're going to add 1 to the exponent, 5 plus 1. Then we're going to divide by that new number, 5 plus 1. Then put a plus c. So you can see it's the same as over here. But really, it's kind of silly to write that. You're just going to rewrite the x, add 1 to the exponent, divide by that number, add c, and whoop, there it is. Whoop, there it is. Come on now. Whoop, there it is. That's our answer right there, okay? And some people are like, how do I know that's the right answer? Well, remember, if you take the derivative of your answer, you'll get the integrand back, okay? So we could actually do a little check here. Check to check it out, okay? And if we check this, let's take the derivative with respect to x of our answer. Instead of writing x to the 6th over 6th, I'll write 1/6 x to the 6th. Put a plus c, so that's a little bit easier right there to take the derivative of. Drop the 6 down like it's hot. 6 times 1/6 is 1. X to the 1 less now, right? X to the 5th, and the derivative of a constant is always equal to 0. And this right here, 1x to the 5th plus 0, just a really complicated way to write x to the 5th. And look, we could see that's our integrand, okay? So that means I actually integrated correctly. This will eventually become counterproductive because the integral is going to get so complicated. Taking the derivative is going to be time consuming, and you might make a mistake. So you really want to practice your integration. Doesn't matter how easy integration looks. It's rough. It's just different from differentiation. You'll see as we go through more problems. There's a little disclaimer here, and that's that n cannot equal -1. There's two reasons. If n is equal to -1, we use this rule. Down here, and we divide by -1 plus 1, right? Because n is -1. You would divide by 0. Can't divide by 0. The other thing that's cool is that n actually is -1. Then it's the integral of u to the -1 with respect to u. And believe it or not, we write that as the integral of 1 over u to the 1st with respect to u, 1 over u. and you might recognize it. That's somebody's derivative in there. Does anybody know whose derivative that is? Usually somebody can come up with it. It's actually ln u's derivative. You might remember when you took the derivative with respect to x of ln x, you get back 1 over x. So if you actually integrate 1 over x, you get back ln x plus c. It's actually ln absolute value x. We'll talk about it next week, just like we'll talk about this one next week right here. So this is next week. So if n is equal to -1, it's actually a different integration formula rule that we need to use. Okay, so it doesn't apply to this situation right here. Remember, the list will grow, but for now, this is what the list is. Okay, how are we doing so far out there? What do we got? Thumbs up, thumbs down, sideways thumb. Remember to vote at home. You better be voting. You know, there are a lot of other things to talk about with integrals, and they're going to seem complicated, but they're really not as complicated as they might seem, okay? You know, we'll go through stuff, but then we'll talk about how it's silly to do some of the things that what we're doing, because it's really just going to end up, you know, causing issues. We'll talk about it, and let's talk about, you know, little star action, little star. You know, these aren't basic integration rules. We can call these like integration properties, like boardwalk and park place properties, right? Props. Does anybody know about Monopoly anymore? Great game. Not as good as Risk. Not as good as Axis and Allies. And they all pale in comparison to Dungeons and Dragons. What? Anyway, so integration properties. The first one bothers people. We do the integral of du. My integral signs are whacked today. People are like, integral of du? What the heck is that? Well, that's just like taking the integral of dx. And that bothers people because in between the integral sign and the dx, that's the thing you're supposed to integrate. And people are like, there's nothing in there. There is. There's actually a 1 in there. So you're just really integrating 1 with respect to x. And try to think about it. That's somebody's derivative in there. So you want to think to yourself, what do you take the derivative of with respect to x to get 1 back as an answer? And very good. If you take the derivative of x with respect to x, you get 1 back. Just don't forget to add some cookies, okay? Put that little plus c right there. So it's kind of silly. It's going to actually get applied more in the second property that we do. You'll see what I'm talking about. But the integral of du, just be careful. That's the integral of 1, not with respect to x, but with respect to u. So that would be u plus c. So you got to be on the lookout for that. It's just really like you're switching variables, and we'll do that with u substitution later in the week. Like the integral of dt, very popular now. The integral, you know, of dt, the integral of 1 with respect to t. You know, you got to think of, what do I take the derivative of with respect to t to get a 1 back as an answer? Don't say x. You got to say t in that case, because dt over dt is equal to 1. Then you add that c right there. So it's kind of silly, but it actually jumps right into this rule over here, number 2, where if we actually put a constant in there, we, you know, instead of a 1, we have some other constant. So maybe the integral of k with respect to u, where k is a constant, it's a constant. All right, so maybe we'll do a little something like this over here. And remember, the concept of a constant connected by multiplication, you could always pull the constant to the side, perform the calculus, and then reattach the constant. Here, this is like an example. We'll do an example at the same time. It's like we're integrating, I don't know, let's do 3 with respect to x. It's the same thing. K is 3 and u is x over here. When you actually have a constant connected by multiplication, you can pull him to the side, okay? And here, we're going to pull him to the side so far, we're going to bring him out of the integral sign. Bring him out, bring him out. And 3 times the integral of dx, we could write it that way. Just like the integral of k du is equivalent to k times the integral of du, okay? You could just take a constant, connected by multiplication, pull them to the side, perform the integral, then reattach, okay? So this is really applying the rule. Why do we do it? Well, now we can perform the integral, okay? We pull the 3 to the side. Now we do the integral of dx. Remember, the integral of dx is just the integral of 1 with respect to x. We know that's x plus c from before. Just be careful. X plus c is a binomial, right? So you want to multiply 3 by the entire thing. But believe it or not, you don't have to worry about this, because when you do distribute, we know 3 times x is 3x, plus you could say 3 times c is 3c, but it's actually not necessary, because just think about it. 3 times a constant is just going to be another constant, okay? You know, if this was 2, 3 times 2 would just be 6, okay? 6 is a constant, just like 3 is, just like 2 is. This is something that we won't speak about a lot, this topic. We'll just really talk about it today. I want you to see it. In the future, you won't have to do it until we get to differential equations next year, okay? It's actually an important concept to know. So if you want to see this, you know, applied again over here, this actually be our final answer. You could notice if you just pulled the 3 to the side and you just made the integral of dx x plus c, you could have just attached the 3 to the x. You didn't have to worry about actually distributing him. Like another example, example here. Let's do one slightly more interesting. Let's do the integral of 2x cubed with respect to x. You know, you don't actually need to show this first step right here that you're pulling the 2 to the side. You don't need to put 2 times the integral, okay, of x cubed with respect to x. You could just pull the 2 to the side and think, oh, now I want to take the integral of x cubed with respect to x. Well, if we take the integral of x cubed, you want to use that formula we talked about down here, right? You want to add 1 to the exponent, divide by the number. You know, so really, we're just going to integrate x cubed, add 1 to the exponent, that's 4, divide by that 4. Then you could just put a plus c on the end. Technically, you want it to be 2 times this entire thing right here. But when you distribute the 2 in, 2 times c is just going to be another c. It's just going to be another constant. So all you got to do is pull the 2 to the side. Like I said, constant connected by multiplication. Pull them to the side. Perform the calculus. Integrate x cubed. That's x to the 4th over 4. Then reattach the 2. So 2 times x to the 4th over 4. You could cancel now, right? Divide by 2 top and bottom. And we can get x to the 4th over 2 plus c, which is a fine answer. Same thing as 1/2 x to the 4th plus c. You can see either of those in multiple choice. Okay, so really, it's up to you the way you want to write that, and you don't need to worry about distributing this constant to the c. You could just worry about doing the entire integral problem, then putting the plus c on the end. Okay, you know, maybe do another one over here. Let's do the integral of 4 radical x with respect to x. You know, people start to get all crazy over here, like 4 radical x. You know, that 4 is a constant. We can pull them to the side. You don't need to actually show the step, but you could show it if you want to. You know, and now, well, I know it's 4, but now I got to multiply it by the integral, you know, of radical x. How the heck am I supposed to take the integral of radical x? All you know how to take the integral of right now is a constant. If the constant is equal to 1, even if the constant is something else, you can just pull the constant to the side and then reattach. You'll notice whenever you integrate a constant, you just put x to the first power next to that constant, or the u to the first power, or a t to the first power, whatever your d whatever is over here. Besides that, the only rule we know is how to integrate one single letter raised to a numerical power. And people freak out. They're like, Berto, you know, radical x, that's not one single letter raised to a numerical power. It is, right? Isn't radical x really x to the 1/2? Okay, so now if you actually want to integrate x to the 1/2, where you rewrite the base, add 1 to the exponent. People are like, I can't do 1/2 plus 1. Well, how about 1/2 plus 2 over 2, which is 3/2, okay? And then you divide by that number. You divide by the 3/2. Then you add cookies to the end. Just like over here, we had x to the 3rd. Add 1 to the exponent, divide by that number. Here we have x to the 1/2. Add 1 to the exponent, divide by that number. Seriously though, you know, only Rourke would actually, Dan Rourke, I'm like, what's his first name? It's Dan, right? Only Dan Rourke would divide by 3/2. The rest of us will actually multiply by 2/3. All right, so it's actually a lot easier you could jump right from this step all the way to this step if you're good, okay? You know, just take it slow at first, and you can see over here, now my answer ends up being what? 8/3 x to the 3/2 plus c, which once again, you could take the derivative of that if you want. You will get 4 times x to the 1/2 back, 4 radical x back, but it starts to become a little counterproductive, okay? So look, you know, we added 1 to the exponent, divide by that number. Instead of dividing by 3/2, same thing as multiplying by the reciprocal, okay? You don't need to skip quite as many steps, but as you get good, you'll be able to skip more and more steps, okay? The third property, so the second property, really, it's one you already knew, right? You know, it's constant connected by multiplication, pull to the side, perform the calculus, reattach. The third property is also one that you already know. You know, remember, in calculus, addition, subtraction, it's good, okay? Because when we add and subtract, we could break up derivatives over addition and subtraction. Can't break up derivatives over multiplication and division. You need product rule and quotient rule, respectively, for those. But integrals follow the same rules, okay? You can break up integrals over addition and subtraction. You can't break them up over multiplication and division. There's no chain rule or product rule or quotient rule. You know, some people call integration by parts kind of like kind of like quotient rule and product rule for integrals. But really, integrals are different, okay? If you see things connected by multiplication and division, there's a lot of different things that can happen. You know, we'll talk more about that on Friday. But if you see functions connected by addition or subtraction, maybe a function f connected by either addition or subtraction, whichever it happens to be, to g, we'll say they're both functions of x or functions of u, so we'll put a little du next to it over there. And the moral of the story here is that you could break up this integral. Believe it or not, this du just like dy or dx, dx, remember dy over dx for a derivative, right? Delta y over delta x. It's just the difference of the y value over the difference of the x values. Du, that's the difference between two u values. It's just a constant minus a constant. It's just a constant. So believe it or not, you could actually distribute it. And you could split up this integral and say, you know what? First, let's do the integral of f with respect to u. And then we're going to add or subtract the integral of g with respect to u. And I know it looks complicated, but all it means is that you can integrate this thing, bring down a plus or a minus sign, and integrate that thing, then put a plus c on the end. We'll make it much more complicated the first go around. Got an example set up here somewhere. Let's do the integral of the quantity x squared plus 1 over x cubed with respect to x. X squared plus 1 over x cubed, all with respect to x. And you can see that now we're integrating over addition. You could break this into two separate integrals. And look, the way we're going to write it out right now, it's going to be the long drawn out method, and then we'll show the quick way you could do it at the end. But really what's going to happen here is first you could do the integral of x squared with respect to x. You better distribute that dx to both. That's very important. Then bring down the plus sign, and now do the integral of 1 over x cubed with respect to x. Don't forget that dx. Everybody's like, oh, that's stupid, you don't need it there. You leave that out in the AP, you're going to lose points. There's a very important reason that dx has to be there. Believe it or not, this x squared represents the height of a rectangle, and this dx represents the base of a rectangle. And if you do height times base of a rectangle, what do you get back? Area. Very good. So believe it or not, this inside here really just represents the area of a rectangle. Now, if you leave out the dx, then it's just the height of the rectangle, okay? And if you want area, you have to do height times base. That's why the dx needs to be there. Now, right now, you're like, what in good heck is he talking about? What rectangle? What is this? We'll talk about that when we talk more about what the integral means, but we got to get the definite integral for something like that. So bear with me for now. Also, two integrals now, you could do them separately, but the second one, we need a little rewrite. This is not in u to the n form. People are like, what do you mean? Let's just add one to the exponent, divide by that number. No. This works. This u to the n right here, okay, it only works. Let me just erase this because I need a little bit of space. Okay, this only works when u to the n is upstairs. Remember, everything is upstairs unless otherwise indicated. So you need the variable base to be upstairs. And we could do that easily by making it x to the negative 3. And now we'll integrate with respect to x. Just like over here, we turn radical x into x to the 1/2. We put it in u to the n form. Now we turn 1 over x cubed into x to the negative 3. We put it in u to the n form, okay? And that's what you want to do. Now even more complicated, we integrate the integral of x squared, add 1 to the exponent, divide by that number. But then you're supposed to add c. I'll put c sub 1. There's a reason for that, because when we do the second integral over here, we're going to get another c back, and it's not necessarily the same c as over here. Just be careful. Rewrite the base, add 1 to the exponent. Negative 3 plus 1 is not negative 4. It's negative 2. A lot of people make silly mistakes. Then you divide by that number. Then you add a constant. I'll say c sub 2. You'll never have to do this again, though, because when you combine like terms, guess what? A constant plus a constant is just another constant. Very good. So you could have just said, oh, x cubed over 3 plus x to the negative 2 over negative 2, and then you just put a plus c on the end. In fact, that's what you should do from this step right here. The first step, if you have stuff connected by addition or subtraction inside an integral, don't split it into many integrals. Sometimes you need to when things are abstract and stuff like that. We'll talk about it more next year. First thing I would do is the rewrite like we did before, and then I go right from this step to this step down here. I'd say, you know what? The integral of x squared is x cubed over 3. Okay, and then I bring down the plus sign. I'd say the integral of x to the negative 3 is x to the negative 2 over 2. And then I just put a plus c next to it. That's all I would do. So you could easily go from here to here. But it's important to know what's happening. There's a lot more, going on than meets the eye with integration. This is disgusting. If you think you'll see it multiple choice that way, you're wrong, Sally. X cubed over 3, you might see. You might also see 1/3 x cubed. That's arbitrary. Either of those you could see. This here, they'll probably take this negative, put it upstairs, okay? They'll bring the x squared, x to the negative 2 downstairs, make them x to the positive 2. So this 2 is going to be chilling down here. This x to the negative 2 comes downstairs, becomes x to the positive 2. Can't leave the upstairs empty. You got to put a 1 up there. And then when you put the negative up there, it's really a negative 1. But if you add a negative 1, you really end up subtracting 1. And once again, stuff that we talked about earlier in the year, and we spoke about exponents, which was not a test that a lot of people did really well on, which does not surprise me. Common Core has made exponents even worse, and they were rough back in the day. People always struggled with this, but make sure you can go from here to here, okay? It's not always just about the calculus, sometimes about the algebra as well. And integration, if you practice it, you will get good, okay? The problem is the basic integration, we'll start you doing U substitution on, Friday. U substitution might sound difficult, but it gets pretty mechanical. If you practice it, you can get really good at it. The problem is people get so good at U substitution, which is non-basic integration, they'll forget how to do basic integration. So let's talk here. Let's get some basic integration going on. Some people look at this problem right here and they're like, wow, everything you hate all wrapped into one. It's really a rude way to look at it, okay? This is the integral right here. It does represent an infinite sum, but it's not necessarily the sum of all your fears. First off, put a little equal sign here, and I won't be afraid. Ask me the questions, Bridgekeeper. I am not afraid. Some people get that. I can see functions here connect in the integrand connected by addition and subtraction, okay, which means I could integrate all of these separately. I can really turn one integral into 1, a 2, a 3, 4, 5 integrals, okay? But before you integrate, ain't it great, you might want to rewrite, okay? And if you're rewriting, you're not integrating yet, which means that integral sign better still be there. Just like with limits, okay, the limit sign had to stay until you evaluated the limit, then the limit sign went away. For some of you guys, you just left it there the whole time, but that was incorrect. For the integral, until you integrate, that integral sign is going to be there. And then after you integrate, then the integral sign goes away. It's like taking the square root of 4, right? That square root sign stays there until you actually take the square root, then it goes away, okay? So the 2x squared is actually in a nice form to take an integral, right? Because I could just pull this side, then 2 to the side, and just integrate the x squared. But the 1 over x cubed, x to the negative 3, we did that a moment ago, minus radical x, let's make it x to the 1/2. Plus x is pretty good because that's x to the first. Then we'll say plus 6 with respect to x. So you might want to get that type of rewrite going on. And then you could make this into 5 separate integrals with a dx on each of them and then get 5 separate c's and combine all those c's. It's going to take you forever to do anything, okay? So really, you can kind of skip those steps and just integrate these separately. To integrate 2x squared, pull the 2 to the side, right? Constant connected by multiplication. Integrate x squared. Add 1 to that exponent. Divide by that number. Bring down the plus sign. That's this plus sign right here. All right, now the integral of x to the negative 3. We know we rewrite x. Add 1 to the exponent. Divide by that number. We did that before. And now we bring down this minus sign. And now we integrate x to the 1/2. Well, we add 1 to 1/2. Okay, so 1/2 plus 1 is going to be 3/2. And you could divide by 3/2, or you could actually just multiply by 2/3. I'll put dividing by 3/2 here just because it's the first day. Then I'll bring down this plus sign over here. But really, a lot of people would jump right into 2/3 x to the 3/2, and that's how eventually you should be able to do it. Integrating x to the first is easy. X squared over 2. Plus, now we got to integrate 6 with respect to x. And you should know how to do it. Remember the simplest way to integrate anything. We kind of get lost in that because we kind of focus on rules for a while. But the simplest way to integrate anything, that's somebody's derivative in there. Whose derivative? The answer's derivative. So what do you differentiate with respect to x to get 6 back as an answer? And that answer is what you want to grow up to be, what you're all going to grow up to be, a success. Okay? If you take the derivative of 6x, you'll see you get 6 back as an answer, okay? Don't put a 0 here. Too often people think the integral of 6 is 0. That's not the integral of 6. That's the, very good, derivative of 6, okay? So be careful with something like that. And then don't forget to put the plus c on the end right there, okay? So what we really have when we clean these things up is you can make this 2/3 x cubed, or you can make it 2x cubed over 3. It's the same thing. I'm going to make this plus a minus because I'm bringing that minus sign up. The 2 is going to stay downstairs. Bring down the x to the negative 2. He's now x to the positive 2. Leave a 1 upstairs. Minus, instead of dividing by 3/2, multiply by 2/3. Okay, plus, you could leave it as x squared over 2, or you can make it 1/2 x squared. That's up to you. Plus 6x plus c. Okay, so pretty nasty answer right there. And people are like, oh, I'll take the derivative to check my work. Go ahead, okay? It just gets kind of annoying to do in these particular types of problems. But these aren't as bad as you might think, okay? You got homework problems tonight. Do the best you can with them. I know it's a long lesson today. It's up to 38 minutes already, 39 minutes in a second, 39 actually in 3 seconds. But tomorrow will be a shorter lesson. All right, so please try your homework. I think it's the ditto, either evens or odds, and we'll do the other ones tomorrow, okay? So integration, remember, anti-differentiation, all right? So try to remember when you integrate, The integrand always represents somebody's derivative. Okay, whose derivative? The answer's derivative. Don't forget about this basic integration rule. Okay, so we know how to integrate, one single letter raised to a power. Don't forget the properties. If you have one single letter raised to a power connected by addition or subtraction, no problem there. And this is really just integrating a constant. Pull it to the side, okay? You want to integrate 3 with respect to x. You don't even need to do it this way. You could be like, hey, that's somebody's derivative in there. What do I take the derivative of with respect to x to get 3 back? 3x. And then just put a plus c next to it. So it's not as bad as you might think. More in the next video. And we'll see ya when we see ya. It's Berto signing off. Adios.